Hey guys, Mr. Santiago again. We're going to go ahead and continue on with Unit 11 notes on kinetics and equilibrium. So please watch the first video if you haven't already done so. We're going to move on, starting with rate laws. And rate laws are simply just equations that help us see the impact when we increase or decrease the concentration of one particular reactant and how it affects the rate of that reaction. Okay, so that's really all it is. In any case, so last video we talked about reactions and how they are reversible. We'll talk about that again a little bit later, but reactions are, many reactions are reversible in general, and, as you make the products can then, react again to turn around and make the reactants, so it can kind of reverse the process. But in any case, we're going to focus only on the reactants in a forward direction because, or we're just going to focus on reactants of any particular chemical reaction because we're going to use what's called the initial rate method. And the initial rate method, if you remember, is when you first put those reactants together. And at that moment in time, when they first touch each other to start to react, there are no products yet. So you don't have to worry about putting products into the rate law equation. That kind of makes it nice for us. We don't have to worry about that. We just focus only on the reactants by themselves. So here's the basic overall format and how we write a rate law. Okay, rate is equal to little k. Lowercase k is the rate constant. That is simply a constant. And again, it's a lowercase k, not to be confused with capital K, which we're going to use for equilibrium later on. So we're going to use lowercase k for the rate constant. It's just a number. It'll be given to you, or you can solve for it if given some data. So little k times the concentration of substance, of some substance, we'll call it A, to the nth power times the concentration of substance B to the nth power. Now remember the brackets, right? The brackets around here mean concentration. And for us, that is going to be molarity for this unit, all right? Not molality or anything else. It's going to be molarity, all right? Moles per liter. So now the exponents, this is what we call the order with regard to that particular substance, A, for example. Now it's just an exponent, like mathematically, like any other exponent. And so, for example, if this is 1, let me get my, my drawing going here. Okay, so let's just say this is 1. Well, then we say that substance A is first order. So it's first order with regard to substance A. If n were 2, for example, then we would say that it is second order with regard to substance B, or reactant B. Okay, and that's all it is. And then the overall order of the reaction, the overall reaction order would be 3. You just add them up, right? You add the exponents up. Okay, so that's how we discuss the exponents. We talk about them as, we call them the order, reaction order. Okay, so 3 key points. The concentration of the products does not appear in the rate law. We talked about that already because they haven't been made yet. In other words, the very moment you put those reactants together and they initially touch or bang into each other, there are no products yet. So we want to use that rate of reaction. And number 2, the reaction order must be obtained experimentally. So you can't just look at a chemical reaction, unfortunately, and know what the reaction order is based on. It doesn't necessarily work that way. We have to get in the lab, do some experiments, and figure it out. And essentially what we're doing is we're just going to change the concentration of one reactant, A, for example. We're going to change A while keeping B the same to see how A affects the rate. And then we're going to do the opposite, right? We're going to change B while keeping A the same to see how it affects the rate. And that's, in general, how the rate law expression is created. That's how we determine what the order is for each of these, to see what their impact is on the rate, all right? The higher the exponent is, the greater the impact change in the concentration of that reactant will be, okay? So let's go ahead and take a look at an example. So here's some trial data. And we have trial number 1, for example. We have ammonium and nitrite. So the concentration of ammonium, let's just say in trial 1 is 0.1. And then we put that together with nitrite at a 0.005 concentration, moles per liter. And then we measure the rate of the reaction, the initial rate. And it turns out to be this value here. So with this starting concentration and this starting concentration, this is the rate of the reaction based on what you started with. Okay. Now, how do we know which one is going to impact the reaction more, or if they're going to be the same? Well, we have to do more trials. So in this case, we have another trial, number 2. And what did we do with number 2? We kept the ammonium concentration the same, as you can see here, but we doubled the nitrite concentration. And then we looked at the rate. And if you can see, the rate doubles, right? If you need to calculate that, you can, but you can probably see it. All right, so keeping ammonium concentration the same, you double the nitrite concentration, the rate doubles. Now, if we take another trial, trial 3, notice we doubled the ammonium concentration while keeping the nitrite concentration the same. So we did the opposite, and then we checked the rate, and it looks like the rate doubled as well. All right, so this tells us what the rate law values are. Now, I'm going to go through, I mean, this math looks a little bit messy, but I'm going to explain it in a real thorough way, just so you get a 100%. I'm probably going too far with this, but at least for honors chemistry. Now, if you're planning on taking AP, you're going to want to pay more attention to this. If you're planning on taking AP next year. In any case, let me go ahead and let's see if I can make this a little bit easier on myself. I'm going to just copy and paste something here. Let's get that up here. All right, so we're going to do this. All right, so again, we're comparing, right? We're comparing two different trials to see when one doubles, what happens to the rate. So you always have to use a ratio between two different experimental trials. So that's why I'm putting two of these up here, because one of them is going to represent one trial. And let me go back to this. Okay, so let's just start off with rates of trial 3 and trial 2. So we're going to look at these two trials here. So let's just say this is the rate of trial 3, and this is going to represent the rate of trial 2. Okay, well, if I'm looking at the ratio of these guys, what are we doing when we're doing ratios? We're going to divide. That's how you get ratios, right? So we're going to go ahead and divide both of these. Now let me just add. This is your This is your M. This is your N. Right. This is your M. This is your N. Okay. So now right away, if you're going to do some division, right away you can see K. It's a constant value. That's going to cancel. Right. No question. That goes away. So if we're looking at trials 3 and trials 2, notice nitrite is the same. So if the value of nitrite, if we plug in 0.01 up here and both here, 0.01 divided by 0.01, right, that cancels. So that goes away. So look at what you're left with. Aren't you left with this? Yeah, we're left with this, right? That's what you're left with. So I know that looks kind of ugly, right? But that's basically what we're left with. Now the 2 and the 3 over here, that just says we're looking at trial 3. And that 2 down here is saying we're looking at trial 2. That's the number for trial 2. That's all the 2 and the 3 mean, okay? Just to match up with what we have over here. Okay, so now that we have that, all we have to do is plug in numbers, right? What's the rate for 3? Well, it's right here, right? There's your rate for 3. Plug it in, right? The rate for trial 2, plug it in. And then the concentrations of ammonium, right? Because the nitrite's canceled, so the concentrations of ammonium, plug them in. So look what happens. This divided by this equals 2, right? Which equals that. This divided by this equals 2, which is that 2 right there. So 2 is equal to 2 to the mth power. So to make this true, what does m have to be? Well, it has to be equal to 1, right? That's the only way this equation would be true. So therefore, we know m is equal to 1. So when we look at our rate law, we can say m here is equal to 1 with regard to ammonium. So let's go back down to the rate law over here. So we know the order is 1, okay? And of course, if your exponent is 1, you don't have to write it. You can leave it invisible. We typically do that because it's just 1, so it's not going to impact the value here. All right, so there's that. Now, what about for n? Well, if we want to solve for n, we're going to do exactly the same thing. Let me get rid of this because that's not going to cancel anymore. And let's let's remove this and remove this. So we're going to for solving for n, we're going to look at this right here, rate 2 and rate 1. So we're going to look at these guys. All right, so let's just say that this represents the rate of trial 2, and this represents the rate of trial 1 over here, okay? Well, K still cancels, so we'll leave that alone. But now, look, ammonium is the same, right? So 0.1, 0.1. If I plug in 0.1 and 0.1 over here, right, that goes away, that goes away. So now what are we left with? Well, we're left with this, okay? And then again, just like up here, we plug in the numbers. Now notice this doubles, right? 2.7 times 10 to the minus 7 divided by 1.35 times 10 to the minus 7. That's going to equal 2. Then you have 0.01 divided by 0.005. That's going to equal 2. So therefore, what does n need to be to make this equation true? Well, n needs to be equal to 1. Okay, and so we know then that the nitrite, with regard to nitrite, right, the order is 1. Okay, so that is your rate law. And of course, again, if it's a 1, you don't have to show it. So I'm going to get rid of this. And that would be your answer here. If you want to solve for the rate law based on your trial data, this would be the rate law for the reaction. Okay. Now the overall reaction order, because this is a 1 and this is a 1, the overall reaction order would be equal to 2, right? Because it's just 1 plus 1. All right, so that's how you can use trial data. Now, I went way more in depth just to show you how the math plays out, and hopefully it made sense. Now, in general, if I were you and I was trying to do a problem like this, right away, before looking at any of this stuff over here, I would say, okay, well, let me just see, let me find where ammonium is the same. So I would say to myself, okay, let me look at trials 1 and 2. This doubles, when that doubles, that doubles. So right away, with regard to nitrite, I know right away that we're going to have this situation. We're going to have a 2 here, okay? And then I'm going to look at, now, so when one doubles and the other one doubles, right, the rate doubles, so that's the rate over here, right? So when one doubles, the other one doubles, so therefore, right, I can solve and say m equals 1. Now, looking at the other one, now, trials 2 and 3, I can say, okay, well, this doubles when that's the same, and looking at the data here, this doubles, so when this doubles, this doubles. So if that doubles, when that doubles, that's your 2 and your 2, so n must equal 1. So without actually writing this all out and plugging it all in, you can kind of just look and say, okay, that doubles and that doubles, that means the order is 1. Okay, so that's looking at trial data, getting the rate law from that. Now let's take a look at solving for K. We have our rate law from the previous example. We want to solve for K now. Well, that's actually really easy. I can pick any one of these trials that I want. Doesn't really matter. Let's just take a look at trial 1, for example. Now, if I want to pick trial 1, it's very simple. My rate is simply equal to this in trial 1. It's already printed for me, right? So all I have to do is plug that in right here. And then we have the concentration of ammonium right here. Plug that in. And then we have our nitrite concentration, which we can plug in right here. Okay, so plug in all those numbers, right, and solve for K. Okay, and I'm sure you guys can do that on your own. Okay, moving on. All right, let's take a look. Now these rate laws, these are called integrated rate laws, and so don't worry about how they were integrated or anything like that, but you will need to know these equations. You need to be familiar with these so that you can solve some problems with these. And so these equations help us do a couple things. They can help us solve for things like half-life, right, which we talked about earlier in the year, right? This should look very, very familiar right here, right? This is what we use to solve for half-life. And all of the half-life problems we solved for were first-order problems, which is why we went ahead and used this equation. But you can solve for half-life with second order and zero order and second order as well, but the equation changes. Okay, so based on the order of, whatever substance, whatever reactant we're talking about, you have to use the correct equation to solve for any problems that you might be given. Now, one quick memory aid that I like to give my students is, going in order, 0, 1, and 2, 0 first and second, we have a term, no log flipping. Okay, no log flipping. Now, log meaning logarithm, right? Here's your log, right? This is the only equation that involves logarithm of substance A. And then this is flipped, right? You have the reciprocal, right? So that's your flipping. So no log flipping is one easy way to kind of help you remember which equation is used for the type order that you're working with, okay? And they're basically, they're almost exactly the same if you think about it. Other than the no log flipping, they're almost the same. You have your final concentration, right, at time t minus your initial concentration equals negative kT. You have the log of your final concentration minus initial concentration equals negative kT. And then you have the flipped final concentration minus the flipped initial concentration equals kT. Now, the only reason why there's no negative sign here is simply because these are flipped, right, and that's going to result in a positive sign there. So that is essentially one easy way to remember equations for the different um, for each order and how they differ. Now, these can be easily converted to y equals mx plus b format when we graph them. So really all you're doing, let's just take zero order for an example. All you're doing is you're taking this algebraically, right? You're taking this and you're bringing it over to the other side, right? You know, basically you're adding the negative concentration of the initial concentration of A to both sides, right? And that will give you the y equals mx plus b format, which looks like this. Okay, so I just took this guy from here to the other side, and there you go. Here's your y, right? There's your k is your m, your slope. Okay, so k is your slope, and then you have the concentration, the initial concentration, which is your starting concentration of y, right? So for example, it'd be like 0.20 over here, which is your y-intercept, right? So that's your b, your y-intercept there. All right, so that's, you can do that, and we do that with all three of these, right, to get to y equals mx plus b format. Now, why do we do that? Well, we do that because if we get some data experimentally and we plot the data, we can plot it in three ways. We can do the no log flipping. In other words, we can plot the concentration by itself versus time. We can plot the log of the concentration versus time, and then we can plot the flipped version over time. Now, because y equals mx plus b is the equation for a line, well, then I can look at all three graphs and say, okay, well, whichever one the line is, that must be the order of my reaction. So again, no log flipping, zero, first order, second order. So the zero order, right, when I graphed the concentration over time by itself, no log, without the flip part, it gave me a straight line. That tells me that this must be the zero order must be the order, right? That it has to be, because when you plot the points, it's got to give you a straight line if you're looking at the correct order. So since these are curved, right, that can't be, this can't be first order, can't be second order. This particular data that we received has to be zero order. Okay, so that's really all we're doing here. And we can do the same thing with first and second order reactions as well. So here is the first order y equals mx plus b equation. And so in this particular case, because this is a first order reaction, it's the first order graph that's going to give you a straight line instead of a curved line here. So here's your no, your log, your flipping, right? If we graph the same data points three different ways, we take the concentration, we take the log of that concentration, we flip the concentration versus time. If we make three different graphs with the same exact data points, whichever one gives us a straight line, that tells us what the order is. Okay, so in this case, since it's the log of the concentration, that tells us that it must be a first order reaction. And then we have second order again, you're just bringing this from the other side, y equals mx plus b, no log flipping. Here's the flipped part versus time. Since that's the one that gave us a straight line here, that means that this data must represent a second order reaction. Okay, so that's all there is to that. So let's go ahead and move on to sample problem number 1. For the decomposition of hydrogen iodide, you have the rate law, so that's nice, they gave us the rate law. Now notice, what does that mean? That means that it is a second order reaction, right? With regard to hydrogen iodide, it's a second order. So immediately I can go back and I can say, all right, well, if it's a second order reaction, I'm going to be using this equation most likely. So I'm going to keep that in my mind. I'm going to use this equation here, okay? All right, so we have our K value also. That's kind of nice. They gave that to us. So we know we have our rate law. We have K. So that tells us we have a second order reaction. That tells us what the value of K is. Now let's take a look at the rest of the information. We have 0.01 moles of hydrogen iodide placed in a 1 liter container. Well, now that tells us if we have 0.01 moles per liter, well, that means that the concentration of HI, basically I can take this and substitute it with capital M, right, moles per liter. So I have 0.01 molar. Now, if this had been a different number, 1.5 liters, for example, well, then you have to divide, right? You have to take your 0.01 divided by 1.5 to get your concentration. Because remember, these formulas, these equations, are working with molarity concentrations. So we want to make sure that we're always using those concentrations in the formula, in the equation. All right, so in this case, it was kind of nice. They left it at 1 liter, so that basically tells us that we have 0.01 molar hydrogen iodide initially placed. All right, now how long will it take for 10% of the hydrogen iodide to decompose or to react? All right, now it says 10% of it reacts. Well, what does that mean? That means if 10% of it reacts, that means 90% will be left. Okay, so I just, so I'm not slow and sloppy, I went ahead and printed the answer key for you so we can take a look at how we can solve this. So if 10% of 0.01 is equal to 0.001, well then the 90% remaining, just subtract, right? Take your 0.01 minus your 0.001 and you're going to get your remaining 90%, which is 0.009. Okay, let me change the color here. Okay, so that's what you're going to get here. All right, so that's your 90%. Okay. All right, so if that is the amount remaining, well, now it's just a matter of plugging the numbers into our second order equation. So we're going to take our 0.009 because this is the amount or concentration after time has passed. So that's going to be this value right here. And you have your original 0.01 molar concentration right at time 0 at the original start. So that's going to be plugged in right there, right? And so, and then you have your K, right? We have K over here, which we can plug in right there. So we have all three of these values. Now we need to solve for T. That's how long it will take, the time, the overall time that has passed. So plugging in the numbers, we get this. Now we want to get T by itself, so we divide both sides by our K value, which gives us this. And do the math on your calculator, and you should get a final result of this. Okay, so there is your answer for sample problem number 1 and how we went about plugging in the numbers to the second order equation. Okay, so let's go ahead and take a look at half-life. Again, this is going to be a refresher for you guys mostly because we've done this already earlier in the year. And so here, let's take a look at the first order equation for half-life. Your half-life represented by T half is equal to the natural log of 2 over divided by K. Okay, so that's how we can solve for half-life. Or if we're given the half-life and we want to solve for K, we can also use this equation for that. So let's go ahead and take a look at sample problem number 2. Methyl isocyanide, CH3NC, is the chemical formula for that. Isomerizes, which just means it changes its structural shape, when heated to give methyl cyanide. So this is what it looks like. Notice, the chemical formula has the same, amount of, atoms in there, but in the same ratios, but the NC versus the CN. It's just a change in shape of the structure of the molecule. In any case, this is a first order reaction. So right there, we know we can use our first order reaction equation. They're giving us our K value, which is nice, and they're asking for the half-life. So if they're asking for the half-life, all we're doing is plugging in those numbers, right, and solving for T half, all right? And so that will give us the half-life, and I'm sure you can do that on your own. Actually, let's just go ahead and take a look at it. I went ahead and printed this ahead of time as well. So here's your T half, natural log of 2 divided by your K value, right? Do the math in the calculator, and you get your answer, okay? So this makes it very simple to solve for the half-life. Now, part B, they want to know how long it would take for the concentration of the methyl isocyanide to decrease to 75% of its initial value. Now, be careful. This is not saying that it's decreasing by 75%, because if it were decreasing by 75%, then 25% would be remaining. But here it's saying it's decreasing to 75%, which means that is your remaining amount, okay? So what we want to do is we want to take that and use that as our ratio. So in other words, when we're looking at our first order equation, you have the natural log at time t minus natural log at time 0. Well, logarithm rules tell us that if you're taking the log of one thing minus the log of something else, well, basically you can rewrite that as the log of both of those as a fraction, okay? And if you look back at our Unit 1 notes way back at the beginning of the year, right, you'll remember that we gave you this in the notes, right, this equation right here. So this is that equation. Now, since they're telling us 75%, well, what's a percent? It's part over the whole, right? So the part over the whole equals 75% or 0.75. So if your part over the whole equals 0.75, that means that this whole thing That's your part over the whole, right? At time t versus at the initial, that's your part over the initial amount. That's your 0.75. Okay, so we have the natural log of 0.75 equal to negative kt. All right, now if I want to get t by itself, I have to divide both sides by negative k, which is what we did here. So negative k is on the bottom, our natural log of 0.75 is on the top. That is equal to t. Do the math through the calculator, and we get our answer, 460 seconds. Okay, so sample problem number 2, again, should just be really refreshing your memory on what we learned in Unit 1, but in any case, I just wanted to take some time to do that. All right, let's take a look at sample problem 3. Butadiene reacts to form its dimer according to the following reaction. Okay, and so here's the chemical equation. They gave it to us. Determine the overall order of the reaction by plotting the following data, issuing first and then second order kinetics. All right, so really that's just a fancy way of saying plot the data. So here you can plot the data for this, right? Just go ahead and make yourself a graph. All right, I'm not going to try to do this all on my own here, but you can graph it, right? You have your concentration, right? Your concentration of your butadiene over time, right? So, okay, so that's what you're going to plot your points, and you're going to connect the dots, right? See what you get. That's what you're going to do. So this, if you get a straight line representing the concentration versus time, that means we got a zero order reaction, right? Because that's when looking at the y equals mx plus b formula for this, right, which is what we're graphing here, a straight line would say, okay, we have a zero order. Now we're going to graph this again using the first order method. In other words, we're going to say, remember, no log flipping, right? So we can actually graph this 3 times. And so we're going to have to do the log of the concentration of butadiene versus time. And then over here, we're going to graph the flipping part, right? 1 over the concentration of butadiene, right, over time. All right, so you're going to graph it 3 different ways. You're going to use these same data points, right, to graph 3 different ways. So basically, you can just kind of go like this, right, and then you can do this. And again, I know it's sloppy, but I'll show you the nice, neat, pre-printed way that I have the next slide here for you. All right, so you're going to basically do your natural log of the concentration, right? I'm not going to just write the whole thing out to save some time. You're going to do your flipped version, right, of this concentration, right, versus time. All right, and you're going to plug in all these values just like you would here. So in other words, you're taking each value right here. That's your concentration. So the natural log of the concentration is going to be natural log in your calculator. You're going to plug in natural log of 0.01, hit enter, and that's going to give you an answer. And then this is where, right here is where you're going to write your answer. Okay. Then you're going to do 1 over this value, and then you're going to write your answer right here. All right. And then you go to the next one, do the natural log, plug in the number, get your answer, and so forth. So you're going to plug in all these numbers, and then you're going to plot each of these based on the graph you're trying to work with. So you're going to use these 2 columns to plot the zero order, to see if it's zero order. Then you're going to use these 2 columns, time, right, versus the natural log, to plot these points and then see if it gives you a straight line. And then you're going to plot time and the flipped version, right, plot that out here and see if it gives you a straight line. Whichever one gives you a straight line, that tells you what order it is. No log flipping, no zero order, log, first order, flipped, second order. All right, so let's take a look. I went ahead and did some of this for you, right? So if you want to try it on your own, go ahead, pause the video. But in any case, I went ahead and did it. So I took the natural log of each of these numbers and I plugged it in. I went ahead and flipped all those, plugged them in. And when graphing, I noticed that this is the data that gave me a straight line. So when I graphed time and 1 over concentration, the flipped version, that's the one that gave me a straight line. So my graph, right, looked like this. Okay, that's what my graph looked like. These guys probably looked, something like, this or something like that. And so this way, that tells me it's a second order reaction. Okay, so there's your answer there. Okay, so that's sample problem number 3. Now, equilibrium state, we're not going to go into that in this video. We will continue with the next video next week, next week's assignments with this. So uh, keep an eye out for that. I will also send a message letting you know when that is ready. In any case, good luck to you. Keep pushing forward. Do the best you can. And I'll talk to you again soon.